This is probably the last lecture of new material from Practical Malware Analysis here. If you go down, the whole semester ends in like a day and a week and a few more days. I'll talk about data encoding today. And then the last class, I'm not going to introduce any new material. I'm not going to have a new lecture. I'll just be here to answer questions. All right. And the data encoding stuff is just talking about the types of encryption malware uses, which is in fact interesting and different than what I'm teaching in the encryption class, because malware is a different use case, and they in fact use miserable low-grade encryption all the time. It really is more obfuscation than encryption. Obfuscation is the term for lousy encryption that is just like scrambling something to make it a little bit harder to read, like scrambling your JavaScript or PHP, but not really seriously hiding it to where a professional couldn't get in. It's less scrambling it. Anyway, so here's the point. Malware is not usually trying to encrypt something so it will seriously resist real cryptographic analysis from a real cryptographer. What it's doing is trying to make it harder for a reverse engineer to get in and for an automated tool to detect it. So they want to remove the strings, things like the command and control center server and other strings. They don't need to totally remove them in some fancy way. They just need to scramble them so you can't easily find them with the strings tool. When it's saving information that it's stealing and then sending it off the network, it would like to scramble that information so that your data loss prevention system won't detect things like social security numbers and credit card numbers leaving your network. So it would like to scramble that data so it's not obvious what it is. And that's the game. It'll hide suspicious strings. So you can use a very simple cipher for those methods, and they often do, so they don't need to use any libraries that would reveal what they're doing or any special constants that would be used by special professional encryption routines. So they might just use simple old-fashioned ciphers, like the Caesar cipher. Just move everything forward a few spaces in the alphabet, or you can extend this to binary easily, move every binary byte, add a constant to it, roll it around so the big ones wrap around to 0 and such. That's perfect. It's easy to write a code that will do this in any language you like. Easy to write code to reverse it, and now the strings will no longer match the expected strings from Malware Analyst or your anti-malware tool. XOR is another very common one. If you XOR things with just a constant 1-byte key, then it just translates every byte to another byte. So you can encode high with a key of 3C. So high is 4849. And so you encode it and it turns into different stuff. Flips a few of the bits. And that will be easy to reverse, and it makes things harder to read. So here's attack at noon, which turns into this mess. Curly brace HH, curly brace delete WF5. It's no longer printable characters anymore after XOR encoding. It's scrambled binary, which won't match any signatures expected. And you just XOR it again with the same key to turn it back. All right, reverses itself. Now, you can actually easily brute force XOR encoding because a lot of files contain a whole lot of zeros. Like here's an exe file, or this is a GIF file, but see all these 12s everywhere? Those are zeros in the raw GIF. So if you use ordinary XOR, in fact, any malware analyst can take a quick look at it and immediately tell this has been XORed with 12. There's 12s all over the place where there ought to be zeros, so you can tell. And by the way, it's a portable executable. This is not a GIF, it's an exe, so it starts with MZ. So these are XORed MZ. So in fact, it's pretty easy to crack. So something that malware often does is use, here's what it should look like. MZ followed by a bunch of zeros, and this program must be run not in MS-DOS mode. There are various tools out there you can download to do it. You can also write a Python tool that will just try a bunch of XORs. Just try XORing it with 01, 02, 03 until you find XORing it with something that turns it into a readable file. And look for a string like this program that you'll find in the header. That's one way to do it. Anyway, what's better than XORing with the ordinary XOR transformation, which reveals the key all over the place, you use null preserving XOR encoding. So you XOR it except if the plaintext is null or the key, skip it and leave that byte unencoded. That is a simple transformation, easy to reverse, and then it will no longer be obvious what you've done. So here's XOR encoded GIF this is exe, I should say, and here's the first bytes of null preserving XOR. Now it has the nulls everywhere. It's no longer as obvious what it is. So that's a cute trick. All right. So you can identify XOR loops by just looking at the assembly code. For example, here you see XOR EDX with 12. It's XORing something with a fixed 12, and usually if you look around, you'll see that it is some kind of loop, although that's the only thing I'm seeing here. You can just look for XOR in the assembly and find occurrences. So there's three kinds of XOR you will find. One thing that's quite common is XOR EDX EDX, where you XOR something with itself. Now when you XOR a binary, every place where there is a 1, you flip the bit. So if you XOR something with itself, the answer is always 0. And if you write a high-level language like C and compile it, if you set something equal to 0, it will typically compile to this command. This command is in fact the shortest and most efficient way to set something to 0. So this does not mean somebody's using Xor encoding. This is just a common activity setting a variable equal to 0. If you have register or memory with a constant, that looks like an encoding loop to a constant. Or you can register XOR a register or memory with a different register or memory reference. Then it's not going to be obvious what you're doing. You could have a multi-byte key, or it could be some other activity. But these are the ones that you'd have to take a look at. They might really be XOR encoding something. And you might want to put it in a debugger and put a breakpoint here, and then see the string appear on the stack, and you can decide whether it's something of interest or not. So here's a graphical view of an XOR loop. Here it's doing the XOR. This is EAX, that's setting it to 0. And there's a big loop up here. This is add EAX1. So I'm actually, now this XOR right here is the one that doesn't matter. This one here is the one that actually does the job. XORing AX with 12, and this loop where it goes up here is where it has a counter of some kind, and it's reading through bytes and XORing each byte with 12. So that's the kind of thing you'll see. All right, you can also use add or subtract to do what I mentioned, the binary Caesar cipher, where you just move every byte forward or back a fixed constant. You can rotate it left or rotate it right, where you just move all the bits to the left and the left bit wraps around to the 0. That just is like doubling a number or halving it approximately. Rote is the original Caesar cipher. You can use multiple bytes for the key, and you can use chained encryption. This is an old technique that is actually quite hard to decrypt by hand. You encrypt the first byte with some system like Caesar, and then you use that byte as the key for the next byte. And that encrypted byte is the key for the next byte. So this is just a way to create a varying key, and you can reverse it. But these are the kind of things you might do. All these are very easy to write with just a couple lines of code, and don't require any constant that you can detect. And all right. Another very common technique is base 64. This has been around forever. The original purpose of base 64 was for email. Email is an ASCII-only medium, and ASCII only uses 7 bits out of every byte. It's only for printable characters. So if you wanted to send a binary file like an image through email, you can't because it uses all 8 bits. So you have to somehow encode binary files in some system with just letters, and base 64 is that system. You use capital letters, lowercase, digits, and then 2 more characters like plus and slash. So you have 64 characters. That's enough to encode 6 bits, not 8. And so then you take your raw binary data and encode it as a bunch of these letters, and it gets longer. Every 3 bytes of binary data turns into 4 characters of base 64. So this SWYG is the first 3 bytes, and the next 4 is the next 3 bytes, and so on. Now you have this blob of base 64 stuff, which is plain ASCII and can be sent through a plain ASCII medium. So people treat this as a form of obfuscation. It's not encryption at all. It's just a resorting of the bytes, 6 at a time instead of 8 at a time. So it looks different, but it can be trivially reversed back to its original value. So here's what you do. ATT 3 bytes with 8 bits in each byte. You then group them by 6. These 6 bytes turn into Q, those 6 bytes turn into V and R and U, so 4 base 64 characters match 3 binary bytes. And so you can encode anything, and you can easily reverse it too. So you can do it online. Here's ATT, you can encode it, turns into QVRJ, and so on. There's all online tools, there's simple Python libraries, you can do it in CyberChef. This is a very common transformation. All right. And sometimes you put equals at the end to indicate that there weren't enough bytes here. So you can really spot Xor strings. They look like this, just a blob of text with uppercase, lowercase, and digits, and a couple special characters like plus in here, and often some equals at the end. It's very obvious to spot base 64, and it's used all over the place. Now again, remember we had Xor, the pure mathematical system, and what malware actually uses is often null byte preserving Xor. You can do the same thing. You can custom your base 64. So here's an example of a base 64 file name or folder name, and here's a cookie that's also base 64 encoded. So those are base 64 encoded values. And you can reverse them. And here you'll see it was sending this, I think, as the cookie. So it's just a number to identify which bot you are in some bot army. And another thing you might do, when you do base 64, they typically put in this string. So this will be a clue that it's happening. Somewhere they're going to have this string with all the 64 characters in order. That's the easiest way to program it. And there you see it. All right. And so here's a custom string. You can use a different string. Like you could take the normal string and take this little a and put it in the front. And now you have the same logic, but this will no longer decode with a standard library to decode base 64. You could use a different order of these, and it's basically base 64 followed by a substitution cipher that changes these characters to other characters. And again, it's not in principle any more complicated. It just won't automatically decrypt with normal tools. That's a simple way to make it a little bit stronger. All right, let's try a Kahoot, which I've got here. This is 126. (13A). All right, hit the wrong button somehow, but it looks like I finally found my way to the right place. Okay. Right. I'll give it a few more seconds. Aha, good thing. All right. All right, so what coding reverses itself? All right, that's Xor. All right. Which one is easily reversed? All of them. None of these are really strong like AES or anything that could really hide data. They're all pretty easy to reverse once you figure out what they are. They're just obfuscation, not real encryption. All right, what coding uses letters, numbers, plus, and slash? All right, that's base 64. All right. And what coding turns 3 bytes into 4 characters? All right, that's also base 64. Okay. So all right. All right, let's get back here. Okay, so then we'll talk about cryptography. Like I mentioned, the strong stuff like SSL and AES, that is real encryption that will really hide data even from, let me get this, even from a serious attack. But the problem is they're complicated. It takes a lot of code. You typically have to use a library, and that means you have to include your library, makes your malware bigger, or you're looking for a library on a system that might not have that library. If you use the standard Microsoft libraries, then it'll be easy to detect. You'll see them importing these functions. And if you use symmetric encryption, like AES, now you have a key you have to hide somewhere, and this is why I'm always giving people trouble about their Android applications. A lot of Android applications do this. They encrypt important stuff with AES, and then they try to hide the key on your phone, which is just a stupid, terrible system. There are much better ways to do it. And the malware has this problem where it's going to hide the key. So if your malware is encrypted with OpenSSL, then it includes no standard OpenSSL library, then you'll find these strings here referring to like the OpenSSL help pages and such. So it's pretty easy to tell that they've used OpenSSL. If they're using the Microsoft crypto functions, you'll see functions like this: crypt require context, create hash, crypt derive key, crypt decrypt, crypt encrypt, and so on. So you'll see crypt or CP or cert on these things. Microsoft names are intentionally pretty easy to spot because they're not trying to hide what they do. They're supposed to be names that suggest what they do. And IDA Pro has a plugin you can add that will look for magic constants, binary constants that are used by encryption routines. It can find any routines that use special constants. However, RC4 and IDEA don't use those. Now, neither of those are the official government-approved encryption routines, but they are open source and easy to find and easy to use. RC4 in particular is small and easy to implement. RC4 encrypts things sort of like shuffling a deck of cards by just reshuffling the bytes around, and does not use any magic numbers. Find crypt 2 will then run and tell you here it found some numbers from DES, so somebody's using DES, the previous official government encryption standard before AES, which is not as strong as AES, but it's perfectly, but it is real encryption though. It's not easy to break if you don't have the key, and certainly you could use it for malware. Here's another plugin that has a wider range of constants and might find more things. So here it's finding Microsoft crypt calls, crypt create hash and so on, base 64 and CRT32. So, it's another tool that finds, it's a PEID plugin that looks for these constants. Another thing you can do is just use entropy. Now, entropy is a measure of the amount of disorder in a string of bytes. And this is also what's called information content. Shannon discovered this. So if you have a bunch of bytes and they're all the same, there's actually no data there, right? If I have 1,000,000 bytes and they're all 0, then I can just describe that as 1,000,000 bytes of 0. It does not contain 1,000,000 bytes of data at all. It contains almost no data. But if the 1,000,000 bytes are all different or pretty much random, then they might contain almost anything. So you do this mathematical operation. you take the probability of a certain value, like from 0 to 255, and then take the probability of that byte occurring times the log of that probability, and add them up, and this is the log to the base 2, and that will give you an entropy of 8. This is the number of bits of information in each byte. So if the bytes are all random, they are full. They have 8 bits of information in each byte, and you cannot compress them and make them any smaller. If the entropy is less than 8, then you could zip it and make it smaller, because some of those bytes don't really contain any information. They're repetitive. So I did this a while ago in old Kali Linux. Binwalk is available to analyze a file. So I just made a file that was a series of objects here. So I made random bytes for the first 10,000, and that's what you see here. So random bytes have an entropy that it prints here as 1. Instead of using 8 bits per byte, it's bits per bit is the way I measured it. So this is full with entropy of 1. This is completely random bytes, so this could not be scrambled. Here's what base 64 looks like, of course. The entropy is 6 bits per byte. And here's base 32 and base 16, which I didn't talk about before, but they're just like base 64. You can take 6 bits at a time and encode it, or you can take 5 bits or 4 bits at a time and encode it. So this will have an entropy of 6 bits per byte, 5 and 4 bits per byte. And then at the end I made 10,000 bytes that are all the same capital A, and that has an entropy of 0. There's no actual information there. It could be zipped and made much smaller. Essentially down close to 0. So that's, you can see what entropy will tell you, and now you can calculate the entropy of a real piece of malware. I also tried some images. A bitmap, which is uncompressed, has actually low entropy, because if you have a whole series of color pixels and they're all white, you use 3 bytes for each one, white, 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 so it's really very repetitive, and as you see, the actual information content is low. If you use GIF or JPEG, they compress the image to make it smaller, and their entropy goes up to much higher, close to completely random. That's why if you have compressed data like GIFs or JPEGs, you can't really zip them again. You can zip them again, but they won't really get any smaller because there isn't any unused space to squeeze out of them. So IDA Pro has an entropy plugin that will find regions of entropy and just let you see them. We've also seen them in PEID. So here you see this region is entropy 6, this region of entropy nearly 0, then 5, then 1. So the 6 is base 64 encoded or pretty random bytes like maybe code, and these low entropy regions are just empty or repetitive things like strings or something. So here's 5.95, that could be a base 64 encoded strings. 7.9 is almost 8, that's almost completely random, so that's probably compressed or encrypted data. And you can also do it with a graph that shows you the color. So if I hover this is at a region of 6.9, this white, then these are lower entropy than higher entropy. So this is a way to just get an idea of what areas of code you might want to look at. So here, for example, DES constants have entropy of 6. They're quite random. Then you have low entropy regions. Here's code with entropy of like 5.4 because assembly code is not completely random. There's some tendency for certain things to occur over and over and over, like move and such, but it's pretty much close to random, so it's got an entropy of like 6. And here's an encrypted configuration file here. This is low entropy stuff, and suddenly a spike of high entropy as there's some data there. So it's one way to guide you through a file. All right, and then you can make custom encoding schemes. This is something a lot of people do when they begin learning cryptography. They learn some simple stuff like the Caesar cipher, and then they try mixing 2 or 3 of these simple schemes, feeling like they've made something strong. And in a way, that's all the really strong stuff like AES is. It just mixes simple things like XOR and rotating bytes and stuff, but you have to very carefully choose those algorithms to make something strong. Otherwise, you make something that's mathematically reducible to one of these simple routines. Anyway, you can just do anything you want, like XOR and then base 64 or anything like that, and it'll just be more of a headache for the malware analyst. So here's a custom encoding of something. If you look at the code, it finds create file and write file A, and then it uses XOR with a pseudo-random stream, which is essentially what AES does. So here it's going to, here's XOR, And there's going to be another Xor someplace in here. Which an encrypted, here's the write file. So it's going to write something here. And I'm not seeing where it did the XOR though. But anyway, the idea is it's using some kind of, EBX to EAX, that's why. Okay, so this is XOR EBX with EAX, and here's where it calculates the EAX somehow. So somehow it has a series of bytes that it's creating, and it's XORing with those bytes. So each byte is encrypted with a different key, according to some pattern, and you'd have to figure out how it's getting it, but it's generating these bytes somehow with this subroutine 40122F. So this is the pseudo-random generator, 401121F. You have to find out what that is, but then you'll be able to reproduce the bytes. So different key for every byte, so you're not going to be able to reverse it easily with just a single byte XOR. All right, so this, again, can be small and non-obvious. You're not using library code, and it makes it harder for the reverse engineer. All right, so there's two ways to decode it, of course. The easiest way, of course, is load the malware in a debugger, and then just put a breakpoint here and let the malware decode it for you. That's the easiest. I've done that a lot with PHP malware and stuff. That's the easiest technique. But if that's not convenient or it doesn't work, another thing you could do is read the code, figure out what it does, and then rewrite it in another language. And this is what you might do for something like ransomware. There's various companies that put out these free ransomware decryptors. If they can analyze ransomware and find some kind of defect in the ransomware, like a hard-coded key or some way to predict the key, then they can write a decoder and publish it, and then people that have been attacked with the ransomware can decode their files without paying the ransom. Of course, that's not as much use as it was a couple of years ago, because modern ransomware attackers now don't just encrypt your files, they also leak them and extort you that way. So even if you're able to recover the files, you often end up having to pay the ransom anyway. All right, so like I say, stop it in a debugger with the data decoded and then find out what's going on. But sometimes that is too hard to figure out. And the other thing is to reprogram the functions. So here's Python to do base64, of course. You just import base64, have a string, and then you do base64 decode string. I use b64 decode, not decode string, but anyway. And here's a null preserving XOR, where you do it if it equals the key or 0, leave it alone, otherwise do the XOR. You can write in any language you like Python or whatever language you know, Java or C if you like it. It's easy enough to write this code to reverse any of these encryptions. And here's a custom base64 script that will go to this custom string, which is different than a normal base64 string. And so then they will figure it out from the custom string. You just find the encoded string here, and then you figure out where the index of it is, and then put that in. So that's why you have this string. So 0 will map to this, 1 will map to that, 2 will map to that, and then you can get the number from 0 to 63, which contains the 6 bits of information you need. All right, then there's PyCrypto. I use PyCryptoDome now. Do I recommend ransomware victims pay the ransom? It sounds what you're saying. I haven't worked in it personally, but all my friends in the business say yes. You just have to pay the ransom. There's usually no other choice. The only case in which you would not pay the ransom is if your company has some really strong principle not to do it, and they're willing to lose millions of dollars to live up to that principle, which happens, but it's rare. Or if you have threat intelligence and you know that this ransomware gang is crooks and they won't give you the key anyway. So this is why what's recommended if you're a company of any size and get hit by ransomware, you should hire professional ransomware negotiators. There are companies that do this, and they can help you negotiate the price, and they also know whether to pay or not. But what I've been told is almost always you pay. Most of them will hand over the key, and you really have to, and you also don't want them leaking it. So people pay all the time, which is pretty gruesome. And that means they're encouraged to do it again. So we're currently in a pretty bad situation with ransomware, where everybody's paying, and that just means they're doing it more. It's a good question. In fact, I tried asking our guests from Mandiant this question: are their customers paying? And they, of course, said, we can't talk about our customers. But, my friends in the industry tell me everybody pays. It's very much like, in Central America, there are countries where they kidnap people all the time. And everybody pays there, too. They don't just let the people get killed. It's the same kind of thing. You don't want to encourage criminals, but in a real situation, everybody would rather pay than suffer the consequences. Anyway, so here's PyCryptoDome. This will do DES and AES and everything else is in there in Python. So you set up the malware in a debugger, allocate memory, load the encrypted file, and just run it with the... you can use the malware's code. You can run just the part of the code that does the decryption by feeding it the input and the output. That's one way to do it. And I've done that in simple languages like PHP, although I haven't done it for these binary type of malware samples. And so here's another decryption script. Open the encrypted file for read, open file for plain text. This is the thing that sets it up in the debugger. This is an immunity debugger script that will prepare it to use just the function at this address, 401.1a9. It'll prepare input and a place to put the output, run it. So this is you can automate the process with a script. All right, so let's take a look at another Kahoot, which is 13b, which is going to be here. Continue. Teach. All right. All right, looks like everybody's here. All right, which one is so weak it's not even considered encryption? Yeah, that's right. Base 64 is just encoding, like ASCII encoding. It's not encryption. It's just a way of encoding data to move it around. It's easy to reverse with no key and no analysis. All right, which one uses names starting with CP? Yep, that's your Microsoft crypto functions. All right, what technique is especially difficult to detect? Yeah, RC4. Doesn't require a library, doesn't have any special constants, not easy to detect. And if a file contains random bytes, what will its entropy be? That's 8 bits per byte. That file is full of information and cannot be compressed. All right. Good. All right.